potential difference then, as we continue about voltaic cells, the potential difference between anode and cathode in a cell is called the EMF, which is short for electromotive force. And it's also known as the E cell, measured in volts, which is based on units of joules per coulomb. Coulomb being a charge, and the joule is the measure of work. So the amount of work that can be done moving a charge is the basis of the volt. When chemists decided what they were going to use as a zero voltage, they decided the standard hydrogen electrode would be the best choice because hydrogen sits right in the middle of the activity series. So when you couple hydrogen with metals, it tends to have a negative charge. When you couple hydrogen with nonmetals, it tends to have a positive charge. So the standard hydrogen electrode is She for short, SHE, has 0 volts by convention, and it is an acidic hydrogen solution, 1 molar, with hydrogen being bubbled through at a pressure of 1 atmosphere. That's the standard hydrogen electrode. It's assumed to have a voltage of 0. So all the other electrochemical reactions are compared to the standard hydrogen electrode. The strongest oxidizers, say like fluorine, which is the most electronegative element, have the most positive reduction potentials, meaning they will take electrons. They're very favorable to taking electrons because they are highly electronegative. So they like to take electrons. I use a little anthropomorphism there. And whereas the strongest reducers, like lithium, have the most positive oxidation potentials because they give away their electrons readily. So the measure of the spontaneity of reaction, as far as we're concerned, is that it has a positive potential. If you see a positive potential in the reaction, that means the reaction takes place readily. If on the other hand you see a negative potential for the reaction, it means the reaction tends to run the other way. Which brings up the concept of free energy. The free energy that's available to do work in a chemical reaction can be quantified by the number of moles of electrons that are transferred, multiplied by Faraday's constant, which has units of coulombs per mole. Basically, it's the charge on a mole of electrons, 96,000 coulombs per mole. If you have a mole of electrons pass by a circuit, that's 96,000 coulombs of charge that passed by. And depending on the voltage that the circuit is operating on, you'll get more or less energy, more or less work being done. So the units of voltage are joules per coulomb. When you multiply all those quantities together, everything cancels except joules. So that tells you it's a measure of how much energy a circuit can do based on the number of electrons that pass by, the amount of energy each electron is carrying, and that's it. The amount of energy each electron is carrying, and the number of electrons that pass by. Okay, so a positive voltage or a negative free energy indicates that the reaction is spontaneous. Now, we recall that all the reactions that are listed in the indices of a textbook or in a reference book are based on standard conditions. What do I mean by standard conditions? 1 molar concentration, and in the case of gases, a 1 atmosphere of pressure. But sometimes reactions occur under non-standard conditions. And then what do? Well, we start off with standard conditions as the basis, and that's why we have delta G naught here. That's the free energy that's available in a chemical reaction based on the standard conditions that it's measured at. But to find out what the energy is, the free energy is under non-standard conditions, we add a term, RT ln Q, where ln Q stands for the equilibrium of the reaction. If the reaction is not at equilibrium, if Q is not equal to K, and it's the same concept as we see recycled from chapter 15 and 17 of our textbook, where we can determine where the equilibrium of reaction is, we can then make some judgments about how much voltage the reaction will generate under non-standard conditions. Walter Nernst modified this equation by dividing both sides by negative NFE, because we recall from the previous board that delta G is equal to negative NFE. Dividing both sides by the negative NF, we get that E is equal to E naught, so the standard voltage minus the changes in the standards of the condition standards. So that the final voltage can be reported by the Nernst equation, once we simplify it, to be equal to E is equal to E naught minus 0.0592 over N, where N symbolizes the number of electrons transferred in the reaction, times log of Q, where Q represents the equilibrium concentrations of the substances involved.
Pay attention,